Okay, today we are going to discuss the binomial theorem. This is something that should be familiar to you from Algebra 2. So let's get started. First of all, if I was there, I would have you find these for me, but to save time, let's just go through these together. X plus 1 to the 0 power. We know anything to the 0 power is going to be 1. X plus 1 to the 1 power. X plus 1. Alright, x plus 1 the quantity squared, we all know is going to turn out to be x squared plus 2x plus 1. X plus 1 the quantity cubed, we are going to get x cubed plus 3x squared plus 3x plus 1. And then finally, x plus 1 the quantity to the fourth, we're going to get x to the fourth plus 4x cubed plus 6x squared plus 4x squared, 4x to the first plus 1. Alright, Mrs. Holman, what was the point of multiplying all of those out? Okay, I want you to take a look at the coefficients of all of our terms. The coefficients, and then our constant on all of those is 1. Okay, so let me show you something that you've seen before. Okay, here it is. This should look familiar to you. This is what we call Pascal's triangle. Okay, what I want you to notice is we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you notice, if you go back to that slide before and you look at the coefficients of all of our terms, they follow this pattern. Okay, so I want you to recognize is that Pascal's triangle describes the coefficient of the expansion of a binomial to a power. Alright, so when we took that binomial to the 0 power, we got 1. Okay, that describes this, what I call the 0 row here. When we took our binomial to the first term, we got x plus 1. Our coefficients were 1 and 1. That describes this row right here. Okay, so on and so forth. So you notice when we took x to the fourth power, okay, here are our coefficients right there. Now, I want you to notice, and I'm sure you talked about this last year, but from row to row in Pascal's triangle, okay, what's the special pattern? All right, if you look at any number, let's say 6, okay, we get 6 by adding the two terms above it. All right, so 10, you see, we get here from adding 6 and 4. So our next row would be 1, 6, 15, 20, 15, 6, 1. Okay, so here is the binomial theorem. It states that when we expand a binomial to a power, so in general, x plus y to the n power, we add up these terms starting with 0 and ending in n. Alright, so you're always going to start with 0 right here. Okay, so notice whatever your power is, that is n. Okay, so you're going to start with n combinations of r, x to the n minus r, y to the r. Alright, so what this means, you're going to start with n combinations of 0, x to the n power, and then y to the 0 power. That's going to be your first term. Then you're going to add n combinations of 1, so on and so forth. And you're going to follow this pattern all the way up until you reach n, okay? You know that when we multiply out our binomial, okay, when we take it to a power, we're going to get numerous terms, okay? So this summation is just describing what the terms are going to look like. As we go through examples, this will become more clear to you than just a bunch of letters, all right? Now we call this This n combinations of r, that's our binomial coefficient. Okay, so go ahead and take a minute to write this formula down so you can reference it when we are doing our examples here in a little bit, and then when you're doing this in your homework. Now, I just said that this n combinations of r is our binomial coefficient. But a couple slides ago, we looked at the coefficients of x plus 1 to different powers, and we noticed that those were numbers of Pascal's triangle. Okay, so I didn't lie to you. They actually both are the same thing. Okay, if you look at Pascal's triangle, it is created by using combinations. So this first row is 0 combinations of 0. The second row, 1 combination of 0, 1 combination of 1. Okay, let's go here to what I call row 3. Okay, because we have 3 combinations of 0, 3 combinations of 1, all the way up until 3 combinations of 3. Okay, so these are your binomial coefficients. Why I am showing you this, I do not expect you to memorize Pascal's triangle. I don't think that it is a good use of your time to sit there and create the triangle so that you can get the coefficients of your terms. Okay, instead, if you can understand what a row looks like as far as the combinations, that's going to be a better use of your time, and you can work more efficiently. Okay, so let's talk about the binomial coefficient. All right, you talked about combinations last year in Algebra 2, both in this section and then when you did your probability chapter. Okay, so you know that it's called a combination. In your calculator, now that you have a graphing calculator this year, this is located in Math under the probability menu, and it's option number 3. Okay. Please understand that we can also write a combination with these parentheses right here. So n combinations of r can also be written like this. This means the same thing, n combinations of r. Okay? So you obviously can practice this in your calculator, but we're going to do one of them by hand. So this 8 combinations of 2. Okay? Let's go up here to the formula for actually finding the binomial coefficient, okay? And this is something that you did discuss last year. But this 8 combinations of 2. So what this is, it's the same thing as 8 factorial over 2 factorial, that's our r, and then n minus r factorial, that would be 6 factorial. Okay, well, when you did your sequences and series packet, we worked with simplifying these factorials. Okay, so we know that 8 factorial is the same as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we're going to write that as 6 factorial. Okay, divided by 2 factorial is just 2 times 1, and then times 6 factorial. All right, so these are going to cancel. And we have 8 times 7 divided by 2, which is 28. Okay. Now, I would like you to do 10 combinations of 3 in your calculator. You should get 120. Okay, so we're actually going to go ahead and expand a couple binomials, okay? So I want you to look back to that formula I gave you, okay? We're going to have a summation of terms, where our terms are going to look like, we have that binomial coefficient, then we have that x to a power and y to a power. Now, that x and y in the formula that you wrote down, that's basically representing the first and second term of your binomial. Okay? So, here we go. You are always going to start with a combination of 0, okay? So this power right here, that's n, that's going to tell you what your combinations are going to come from and what powers you need to start with. So we're going to start with 4 combinations of 0, all right? And then your first term in your binomial gets raised to that same power, that 4 power, and your second term would be raised to the 0 power. Okay? Then your next term, you're going to add 4 combinations of 1. All right, we're just going to increase. So now 2x is going to be raised to the third power, and negative 3 is going to be raised to the first power. Okay. Then we're going to move to 4 combinations of 2. 2x is now raised to the second power. Negative 3 is now raised to the second power. Our next term would be 4 combinations of 3. 2x is now raised to the first and negative 3 to the third. And then finally we have 4 combinations of 4. We know we're done because those numbers now match. 2x to the 0 and negative 3 to the fourth. Alright, so this is what I want you to notice about each term. Okay, first of all, we start with 4 combinations of 0, and we go all the way until we have 4 combinations of 4. Alright, we can't do any more combinations, okay? Now, we always start where our first term in the binomial is raised to that same power, alright, and the second one will be raised to the 0. Okay, I want you to notice in all of these that the exponent on the first and second terms within a term are going to add to be your original n. So 4 and 0 here make 4 and 0 here make 4. 3 and 1 here make 4. 2 and 2, 1 and 3, 0 and 4. Okay. The second thing I would like you to notice is that whatever the exponent is on the second piece is going to match whatever numbers right here for your combination. Alright, so here in your fourth term, your negative 3 is being raised to the third power, and you have 4 combinations of 3 associated with it. Alright, I want you to remember those little tricks, because eventually I will ask you to find a single term instead of expanding out an entire binomial. Okay, so you'll need to be able to recognize that pattern so you can do that without expanding the entire binomial. Alright, so let's go ahead and rewrite this and simplify it down. Okay. So 4 combinations of 0 is 1, and then we have times 2x to the fourth is 16x to the fourth, times 3x to the 0, or excuse me, 3 to the 0, which is 1. Alright? Plus 4 combinations of 1 is 4, and then we have times 2x cubed, and then times negative 3 to the first. 4 combinations of 2 is 6. 2x, the quantity squared, is 4x squared. And then we have negative 3 squared is 9. 4 combinations of 3 is 4. And then we have times 2x to the first. And then we have times negative 3 cubed. And then finally we have 4 combinations of 4 times 2x to the 0 times negative 3 raised to the fourth, which would be 81. Couple things to be careful here. Don't forget that that negative is being raised to a power with that 3, and so when it's raised to an odd power, it's going to stay negative. When it's raised to an even power, it becomes positive. Second thing to be careful of is that 2x being raised to a power. It is really easy to forget to raise that 2 to the power as well as the x, so please be very careful, and I would always use parentheses when you're writing out your binomial expansion. Alright, so to simplify this, we're going to have 16x to the fourth minus 96x cubed plus 216x squared minus 216x plus 81. Now, while some of you are complaining that you think that was a lot of work, just think about how awful it would be to multiply 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x minus 3. Okay, that's a lot of work. There's a lot of room for error, where this is a lot more efficient, and we get to the answer a lot quicker with less room for error. Alright, here is the next one we are going to do. So notice that n is now 3, and we have our term x squared plus 4, or we have x squared plus 4 being raised to that power. So, since our n is 3, we're going to start with 3 combinations of 0, and then we're going to take that first term and raise it to the 3 power, and that second one raised to the 0 power. Then we're going to move to 3 combinations of 1. X squared is now going to be raised to 1 last power, and 4 is going to be raised to 1 higher power. And then we're going to move to 3 combinations of 2. X squared is now to the first, and 4 to the second. And then finally, 3 combinations of 3. We're going to write that down here. Plus 3 combinations of 3. We have x squared now to the 0, and 4 to the third. Okay, remember we start with 3 combinations of 0, and we go all the way until we have the same number in our combination. Okay, and then our first term gets that n power, and each term it's going to decrease by 1. Our second piece gets the 0 power, and each term it's going to increase by 1. Alright, so we have 3 combinations of 1 times x squared cubed times 4 to the 0. Then we're going to add 3 combinations of 1 times x squared squared times 4 to the first, plus 3 combinations of 2 times x squared to the first times 4 squared, and then finally 3 combinations of 3 times x squared to the 0 times 4 cubed. So we have x to the 6th plus 12 x to the 4th plus 48 x squared plus 64. Now, I am not going to make you do an expansion of something to the 7th, 8th, 9th power and above. Alright, probably not even the 6th power. However, it is possible that I would ask you to find a certain term in a binomial expansion. Now, what I want you to notice, back here in this example, when we found our first term, our binomial coefficient was 4 combinations of 0. Our second term had a binomial coefficient of 4 combinations of 1. So when we come back here, I'm asked to find the 6th term of a plus 2b to the 8th power. Now, if the first term is going to start with 8 combinations of 0, then our 6th term would actually have the binomial coefficient 8 combinations of 5. Okay, now we know that a needs to be raised to a power and 2b needs to be raised to a power. Now remember the trick that I showed you. Whatever this number here is in your combination, that is what your second piece is going to be raised to for a power. And we know that these powers should add together to be 8, so since this has a power of 5, this must have a power of 3. Okay, so this is our 6th term. So 8 combinations of 5 is 56 times a cubed times 2b to the 5th is the same thing as 32b to the 5th. So our 6th term is 1792 a cubed b to the 5th. Okay. The second kind of example you may see in your homework is asking for the coefficient of a specific term. So here I want the coefficient of a to the 6th b to the 5th. Okay? And here is my binomial raised to a power. Now, if I want b to the 5th, okay, first of all, we know that this has to be 11 combinations of something times 3a raised to the sum power times negative 2b raised to the sum power. Okay? Now, if I want b to the 5th and a to the 6th, okay, we can obviously just go ahead and fill those in as is. Alright? So here I have a to the 6th, b to the 5th, and then whatever my second piece is raised to, that is going to be my combination here. So we have 11 combinations of 5, that's 462, times 3a to the 6th is 729 a to the 6th, times 2b to the 5th would be, negative 2b to the 5th would be negative 32 b to the 5th. Okay? Now, all I care about is the coefficient. So, when you answer this for me, you are going to tell me that your coefficient is this. And I got that by just multiplying these together, but since it's the coefficient, I really don't care about a to the 6th and b to the 5th. Here is your homework. Please use your time wisely, and any questions you have, you can work together to figure out. You can ask the sub, or you can ask me tomorrow if it doesn't get answered today in class.